Hello, this video is the disk and washer method for finding volumes of solids of revolutions. In other words, you're taking a two-dimensional shaded region and you're revolving it around either it can be the x or the y-axis, or it can be any horizontal or vertical line you can revolve it around, which will then create a three-dimensional shape, and the formula that we'll use will find the volume of that. So you can kind of visualize how this triangle revolved around the y-axis would then turn into a cone. And then here's like part of an ellipse revolved around there. Stewie's head fits right in there. There we go. And it was technically formed what's called an ellipsoid, which if you take Cal 3, there's a chance you'll see some stuff with also with volumes of ellipsoid and things like that. So, all right, so let's see how this is done. And we'll talk about what's disk and what's washer. Now, basically, the disk method means you when you revolve your graph, there's no gap or space left in it. For example, let me go back up to this triangle and show you that this would be the disk method going around the y-axis. But now you sort of have to use your imagination here and visualize this triangle. If it was revolving around the x-axis, it would come down and you would have a shape like this, and then circular all the way around, so it would be like a volume. Oh, excuse me, I drew that wrong. It's this way, like so. There we go. And that we find that volume. You see, there's this empty space right in here, and what we'll talk about. That's what washer means. It means it's a volume that has a gap or space in it. But we will get to that shortly. Well, let's focus on the disk method first. So here are the two formulas we use, whether it's horizontal axis of revolution or vertical axis of revolution. I pretty much stick to the x and y axis, but it's can be done. Like, for example, you could revolve it around the line y equals 1 or something like that. Now forget about this bottom part, but then you would have a gap here. That would actually be a washer method. And then it would go down like this, and you have a space in between these two. Or it can be, revolved around any vertical line, such as x equals 1 or x equals 2 or whatever. So it's not just x and y axis, but that's pretty much what I stick to in my problems. But that's all it would be. It would just become a washer method if you revolve it around something else. In this particular case. All right, so r of x just basically means your equation y as a function of x. The r has to do with radius, which I'll talk more about because we're going to have a upper r and lower r whenever we get to the washer. A to b, your limits of integration, and you figure anything moving in a circular fashion, it's not surprising that pi is part of the formula. So we have to square that formula, and then so they're from a to b. And then if it's a vertical axis of revolution, your equation must be a function of y. So if it's y written as a function of x, you would then have to perform the algebra necessary to rewrite it as x as a function of y. And you'll see that coming up shortly. And c and d represent vertical limits of integration. So a and b, like for this one, would be 0 to 2, and c and d would be 0 to 4. So this question is saying find the volume of the solid by revolving the region around the x-axis. Okay. So there's our equation, y equals 4 minus x squared. That is our big R of x right there. And the x-axis, we're going from 0 to 2. This bar just indicates where it's revolving. When you see the bar vertically, it's actually going around the x, and then when the bar is drawn sideways, it's going around the y. But, my problems will always say which axis. You don't have to rely on interpreting that picture. I would always say it like I do right there. So to evaluate this, just be pi times 0 to 2, 4 minus x squared squared. Now, it depends on what your instructor wants you to do. If it's me, I usually don't care for these kind of problems if you use the numerical integration features of a graphing calculator. I don't like calculators that can do things symbolically, integrals, but I don't mind that it can do numerical integration. So you can use that. All right, here's something very important. I'll see people make these kind of mistakes. I wouldn't bother to put this here if no one ever made this mistake, but the last thing you want to do is make silly algebra mistakes. So Stewie's telling you that this is absolutely wrong right here, and it is 100% wrong. So it would be, you actually just FOIL it out. 4 minus x squared times 4 minus x squared. And you get 16 minus 8x squared plus x to the fourth. Now, I'm not going to spend a lot of time explaining all this. This is just basic antiderivative stuff from Cal 1. I'm just going to focus on the setup. If you wanted to ask me about it, I guess you could, but it's just plugging the numbers in there, basic definite integral stuff here. We're not using any fancy techniques or whatever, so you're just taking each of these antiderivatives. I'll just look at this one real quick and then not worry too much about the other ones. So the antiderivative 16 is 16x, and 8x squared would be 8/3 x cubed. Just using the power rule, x to the fourth would be 1/5 x to the fifth. Put in 2, put in 0. 0 will be 0, so I don't even have to, it's basically, minus the big old 0 there. And, if you're required to get the exact answer, which sometimes I make, on handwritten tests, I'll ask for the exact answer. A lot of times the calculator will get it, but sometimes it won't. But anyway, there it is, putting in the more modern operating system of the calculator. I'll show you the F and int command if you're still using this is the middle of 2018. If you're still using a TI-83 that has the F and int that doesn't have the fancy integration symbols. Now you see what I did here though. Notice the integral. I didn't bother to put pi in the integral because I wanted to get the exact fraction. At some point the calculators might become sophisticated enough to where they will show pi, like this. So what I did is just did the integral without pi, and then knowing I would have to attach pi to the answer. Okay, so this is just simple algebra, getting common denominator. And then there we go, 256 pi over 15 would be your volume. Now we're going to take the same graph, which I just kind of put here now. It's the same one up there, y equals 4 minus x squared. I'm going to revolve it around the y-axis this time. I just drew that little bar just to kind of show you that, like that's the way they do it. But like I said, the fact that it tells you the y-axis, that's good enough. I guess I could have also, of course I'm doing this freehand, so I'm not using a stylus, but because I could have also done the little arrow. That's why this looks so bad. I'm not writing. I'm using the mouse. Yeah, I could also have done that, but frankly, as long as it just tells you where it's revolving, you don't need to see that. All right, so since we're going around the y-axis, we need x to be a function of y. So I have to take my equation y equals 4 minus x squared, do a little algebra, solve for x. Technically, x squared would have two solutions, a plus and minus, but since we're in quadrant 1 where everything is positive, we don't need both of those. We just need the positive answer. So x equals the square root of 4 minus y. Now, the last problem, the limits of integration were 0 to 2, but now the limits of integration are vertical on the y-axis. So it starts here at 0, comes up there, and there's 4 right there. So it's going to go from 0 to 4. And then our new function in terms of y, square root of 4 minus y squared dy. And that was actually easier than the last one if you worked it out manually, because the square kills square root, or square root. Yeah, there we go. So this leaves 4 minus y, antiderivative 4y minus 1 half y squared. Plug in 4, plug in 0, we get 8 pi. And you see I did this in the calculator. And there, this time I wrote the time, I didn't for the other one, but there's the fact that it's times pi. So the answer is not 8, it's 8 pi. Now, one thing you'll see me do coming up in some of these other problems, yeah, I used variable y here, but if you're just setting up an integral to be evaluated, and obviously it was important that we got x equals the square root of 4 minus y right here. That was important. But when you're just doing the numerical evaluation on the calculator, you can use variable x there. So you just do the square root of 4 minus x squared dx. That would be all right. I guess I just changed it to y just because, but it would work if you did it with x, as long as it was the right function there, that square root. All right, here's an example where we're going to find the volume of this line, y equals 3 minus 2x in the first quadrant. We're going to revolve it around the x, and then we're going to revolve it around the y. And actually, that's going to form two different shaped cones. Okay, so here's the formula. Now I need that intercept on the x-axis. So I just set y equals 0, so it's 3 halves right there. So we're starting at 0. We're going to 3 halves. So the integral will go from 0 to 3 halves of our function 3 minus 2x squared. So if you're having to do this manually, you want to say manually, you might without a integrating type calculator. You have to square it. Don't do the Stewie thing there. Make sure you FOIL that out to get these 3 terms right here, and then easy antiderivative right there. 3 halves can get a little messy plugging in there. Hopefully you're allowed at least some sort of basic calculator to do that. That would be nice. But anyway, plug in 3 halves, plug in 0. You work all this mess out right here, and it comes up to be 9 halves pi. Now here's what I was mentioning a few minutes ago about if you were using the older calculator that does not show the integral symbol. It's still the f and int function. F and int in the calculator now brings up the integral. But before, you had to do it this way. So you see what you do is you put what function you're integrating. I decided to bring up the calculator for a minute. 3 minus 2x all squared, so I've got that in parentheses, comma x. That just goes in there. X means your variable of integration. So obviously the x has to be whatever your variable is. They have to match. Then you put lower limit 0, upper limit 3 halves, 4.5, which is 9 halves. And of course I didn't put the pi in there. So that makes it 9 halves pi. So if you go math 9 f and int, yeah, see now the modern f and int brings up the integral. The older f and int just brought it where you had to enter the syntax in there in a line like that. So either way, not too bad. Now suppose we're revolving this around the y-axis, since the horizontal bar means it's going around the y. So we have to take our equation y equals 3 minus 2x and solve it for x in terms of y, which is easy algebra. So x equals 1 half times 3 minus y. All right. So now we will be integrating the function 3 minus y divided by 2 squared. And then vertically it's from 0 to 3. 0, 1, 2, 3. You can put 0 in there for x and see real easily that y equals 3. So 0 to 3. And then now what I did was, since that 2 is on the bottom, I squared that 2 to make it 4. and then brought it out with a pi to make it, yeah, I wasn't going to create fractions and then square the whole thing. So I got the 4 out of there. So all I'm doing now is just squaring 3 minus y. Of course, you're putting this in the calculator. Oh yeah, notice I did the F and N with X right there. And for some reason I did it with Y. But still, I could have put X in there. If you put X in there in that same place, it's okay. All right, pretty easy to work out the integral. Main thing is getting the problem set up correctly. The integral should not be too bad. So this one ends up being 9 pi over 4. The other one was 9 pi over 2. Now, because both of these form cones, geometric figures, we already have formulas for their volumes. And just for the fun of it, there, and you don't have to worry about any of this if you're, one of my students there, but I don't would that. But this is just showing using the formula of a cone, 1/3 pi r squared h, and then I put the numbers in there, and then they equal the 2 answers that I got by integration. But obviously, every time we do a problem, it's not going to fall into some famous geometric shape, like a cone or a sphere or something like that. So if that was the case, the calculus would not be needed. But I just want to show, since that was one that did lead to a famous geometric shape, I wanted to show that using these formulas that it was right. Okay, but I wouldn't worry about that unless you want to look it over. Volume of a solid of revolution, Washer method. Washer method means there's a gap in it. You're finding a volume that has some sort of gap in it. Now this is like a typical, washer that you'd use with, screws and things like that, and nuts and things like that. Now so say we're trying to find the volume, of this inner part right here. Now that's assuming it's 3-dimensional, of course, but anyway. The capital R of X represents the outer radius, and little r of X is the inner radius. Now look at this formula. It's Rx squared, big Rx squared minus little Rx squared from A to B. So let's kind of see what's happening here. So what we're doing is we're finding the volume of this entire outer part, all the way, the whole thing, using big R of X. Little r of X finds the volume for that empty part. So what we're doing is, if you take the volume of the whole thing going all the way to the outer edge, you subtract the inside empty part, by default, you're going to be left with what you want. So that's how it works. You identify the outer radius, the inner radius, and then you subtract. Now this sometimes, like I said, the math is not difficult for this stuff. But where people make mistakes is, and that's when, when I get to, especially when I look at in a face-to-face class, you can see that they'll treat a problem as a disk method and not realize it should have been a washer method, because they didn't visualize. It's a little bit of visualization on this, looking at it and seeing if it's going to have that gap or not. So that's basically the skill, but the math part is not too bad. It's not. And there it is for Y. Kind of what we'd expect it to look like. But let's look at this little shaded region just to show you. So just imagine if you revolve this around the x-axis and it came down here. That would not be a washer. It would just be a complete solid, one sort of a part, half circle looking, half sphere looking thing, excuse me. It's 3 dimensions when it's rotated, so it'd be a spherical deal. But now you have to imagine this thing revolving around the y-axis, and it's going to leave that gap right in the middle. So if we calculate the volume from the y-axis to that outer line, which graphically, if you take a vertical line and you revolve it, you're creating what's called a cylinder. And then we're subtracting off, the empty part when it revolves around. The formula creates the other side automatically. So you have all this. So you're taking the entire outer cylinder part, subtracting off the empty part, and by default, that's going to leave you the part that you want. So that's what I'm saying. You got to look at the picture and you got to pay attention to which axis it's revolving around. Then you can determine whether or not it's washer or disc, depending on whether you think there's going to be a gap involved if it revolves around. All right, let's take a look at this one. Find the volume of the solid bounded by y equals the square root of x minus 2, the x-axis, and the line x equals 6, and we're revolving it around the y-axis. All right, let's see. Okay, now, so it's going around the y-axis, so can you see there? So there's the calculator would not graph the line y equals x equals 6 because it won't graph vertical lines in rectangular coordinate system. Later on, we'll talk about the polar coordinate system. You can actually make the calculator graph a vertical line. But anyway, so there's the y equals square root of x minus 2. Obviously, would start at domain would start at 2, and then so we're looking at this region. So this region, if it went around the x-axis, no gap. It'd be a disk. But going around the y, it's going to have that space right. Of course, it goes to the other side. But I mean, so just that space with the other side is going to have all that emptiness right there. This is very similar to this last picture right here, except it's just starting a little bit further away from the y-axis. Okay, so the big R of y is x equals 6. I mean, x equals 6 is a constant function of y. Just like if you have y equals 5, that's y. That's the same thing as y is a function of x. It can be a constant function. So same thing here. Just because you don't see a y there, x equals a number is a function of y. That's your outer radius, the cylinder part. And then the inner part. Now, I have to get x in terms of y, so we have to solve this. It's not too difficult. Square both sides. Gives you y squared equals x minus 2. And then move the 2 over, and you have x equals 2 plus y squared. Because, they both have to be either, for y, they have to both be x equal and x equal. For x, they would both be y equals. All right, so you get this thing set up right. You can use the F and N in the calculator. But if you're doing it manually, it's not too bad. And here's what I've been talking about a few times here, that you can use X in a calculator just to show you. So that's probably the first time I did it with an older calculator and did it with just put Y in there. And then I just did it with the newer F and N and just use X as the variable. Same answer. But the outer, so it's outer minus inner. It doesn't matter which, you might think the y squared plus 2 is so powerful it has to go first. That's not the logic behind this. That's not the reasoning. The outer is the 6, and the inner is the curve. So the inner goes second. So it's 6 squared minus y squared plus 2 squared. So there, so once you have that, it's going from 0 to 2 vertically. Whereas, you can, if you're not sure what that y value is, like for example, we're trying to figure out where those two graphs intersect. If you put 6 into this right here, y equals the square root of 6 minus 2, y equals the square root of 4, therefore y equals 2. So that, you can probably eyeball it and see that it's 2, but that would guarantee that it's 2. Alright, so you have to FOIL this y squared plus 2 out properly. So the 36, 6 squared, minus every term in there then is affected by that minus. They all become negative, so that makes this 32 minus y fourth minus 4y squared. And just, simple antiderivative power rules here. Easy enough. And you'll get 704 over 15 times pi. But you make sure that you include the pi. If you do it the way I did in the calculator, realize the pi goes with it. There it is. So now this same problem is going to go around the x-axis. We know it's going to be not going to be a washer. It's going to be just a disk. And this one's actually pretty easy. You just take the original function, square root of x minus 2 squared. Let's look at the limits of integration. They're going on the x-axis starting at 2 and then goes to 6. So 2 to 6 would be your limits of integration. And that's a pretty easy integral. Square kills square root. I didn't even do the f and n for that one. I just worked this one out, looks like, because they're just so easy. So the antiderivative of x minus 2 is 1 half x squared minus 2x. Plug in 6, plug in 2. Get 18 minus 12 minus, you get 2 minus 4. 6 minus a minus 2 is 8, so you get 8 pi. Fantastic. Now here's one where we're actually crossing over into the other quadrant. Now if we were revolving this around the y-axis, there would be no need, because if you just, when you take the right half of this shading and revolves, it would take care of the other side automatically. But since that's, so I wouldn't even have done this way if we were going around the y-axis. I would have only shaded just part of it. But here, so this is going around the x-axis. So you know, where, I mean, you can still do it with only half of it, but obviously this is going to double your answer, because now we're including both sides, and it's going to revolve the whole thing. So the parabola is y equals 4 minus x squared, and then y equals 3 is our other line. We're still revolving around the x-axis. Yeah, it's kind of interesting though, because let's say if y equals 3 was this boundary and we were revolving around y equals 3, then you would end up with a solid that looked like an ellipse. You'd end up with that if it was being revolved around there. But no, it's still being revolved around the x-axis. So there's going to be a big old gap down here. And I found just a picture. It doesn't exactly represent this graph, but it gives you an idea of what this would look like. It would be this kind of thin, sort of look like a men's wedding band there or whatever. Obviously it wouldn't be at that angle, it'd be straight on, but yeah, so it would kind of curve around that way. And anyway, sometimes it could be tough to visualize what it's going to look like, but so it would have that big old circular gap in there. All right. And you see I've labeled these. The outer radius is the curve, the big R, because it goes all the way to that outside part. The inner radius is the line y equals 3. Now, what I did here to find the limits of integration is, you know, if you think, I mean, you think you can figure it out without doing this math here, that's fine. But I just set the two equations equal to each other and just solved them algebraically. And I got plus and minus 2, which is kind of, you know, kind of what it looks like anyway. Yeah, because another, you could also, without solving them, you could say, I think it's going to be negative 2, and you can plug it into this equation, and you put negative 2 in there, and you're going to get y equals 3. So that means they're going to be y equals 3, y equals 3. Same thing, if you put positive 2 in there, you'll get y equals 3 and y equals 3. Okie doke, so outer, the curve, inner, the horizontal line. Okay, I'm not going to go through all the gruesome details on this one, but once again, it's like I said, it's just basic Cal1 antiderivative. And it yields that answer, which so does the F and N in the calculator. 272 pi over 15. Let's take a look at this one. We're going to find the solid by revolving it around the x-axis, bounded by y equals x squared plus 1 and y equals 10 in the first quadrant. meaning I'm not crossing over to the other side. But obviously we're revolving around the x-axis. This one, you have to be able to visualize that it's going to be a washer. You have to look at it and go, okay, see where that little r of x, that's what you're looking at, where the gap is. And that gap's going to come around, and that's what makes it a washer. Versus obviously, if this was going around the y-axis, it would be a disc. It'd be a solid. It'd be no washer. So the outer radius is the horizontal line y equals 10, and the inner radius is the curve x squared plus 1. Now you see over here I put this scaling. I don't know why I did it this way. Maybe it looks better. So I don't know, whatever. But kind of tricky. Yeah, you got to see the scaling there, or that could have been confusing. But mathematically, because it's hitting between two numbers, but since they go by twos, 3 is between 2 and 4. So, but super easy if you set them equal to each other, x squared. We don't care about the negative 3. So x is obviously 3 right there. Right there. So it's going from 0 to 3. Okay. Now, so the outer is the line, 10 squared, minus the inner, x squared plus 1 squared dx. Okay, so I'm going to kind of skip through a lot of the math here, because like I say, the key on this is the setup. But make sure you square that. If you're having to do it manually, that you square this binomial correctly, like I did right there. The minus will affect everything in the parentheses. 100 minus 1 is 99, minus, minus. Then just use the basic power rule idea. Put in 3, put in 0. You'll end up with this mess right here. And then when you get a common denominator of 5 right there, and subtract it. So 5 times 279 would be 1395, I believe. Subtract 243, you get 1152. And there it is, 1152 over 5 times pi. And there you see the f and f without the pi. Now here's the same function revolving around the y-axis. So as I've already mentioned, this is going to be a disk, solid, no gap. And but though we have to change this to x in terms of y, because the function has to be x in terms of y if you go around the y-axis. So just take y equals x squared plus 1, move the 1 over, make it negative, take the 2 square roots. We don't need both answers. You'll never need both of these. Just one is fine. Because like I said, the whole formula is built into the idea of it already revolving and including the other side. So you don't have to have two equations. Okay, pretty easy interval here, because anytime you have that square root, the square kills square root. So square root of y minus 1 squared. Oh, let me talk about the limits of integration. Go back up here. We start at 1, and it's going to 10. So the line y equals 10, and it's 1 because you put 0 in there for x. Here, 0 squared plus 1 is 1. So it's going from 1 to 10. That's how I knew that. Y minus 1, 1 half y squared minus y. From 10 to 1, 1 to 10, however you like to say it. So you see I put in the 10, I put in the 1. Did a little razzle dazzle there. Well, it looks like I temporarily forgot to put the pi right there with all this, but okay, as long as you realize it's there. So I should have had parentheses around there to do it properly. That's okay. I'm sort of being nitpicky now. Oh, that's a weird looking pi. But anyway, so you just do that and then make sure the pi is there with it at the end. Alright, well that concludes the video on volume, solids of revolution, disk, and washer method.